So, let us come to two dimensional heat conduction. It is your 32nd class on the transport phenomena. So, we will go through the Laplace equation in today's class. Laplace equation. Basically, this Laplace equation is a two-dimensional heat conduction equation in steady state condition. This equation is represented as day by 2t by day by x2 plus day by t plus day by y2 is equal to 0. If you go through the solution of this equation, so that solution itself will provide you the temperature distribution in a two-dimensional plate. So, the solution of the equation number 1, will give you the temperature distribution in a two-dimensional body can be obtained. You can obtain a temperature distribution in a two-dimensional body such as a rectangular plate, a square plate or a triangular plate, whatever the shape may be. So, the next thing is, what are the different ways to solve this equation, the partial differential equation number 1? Methods for solving this partial differential equation number 1. The different techniques are number A, the analytical method. Number B, the numerical method. And number C is the geometrical method. These are the three methods by the virtue of which you can arrive at the solution of the equation number 1. So, in the today's class and in the coming class, we will try to visit three types of solution technique for the differential equation number 1. Now, let us come to the analytical method, that is the number A, the first technique, that is analytical method. So, number A, This technique is based on the separation of variable method for solving partial differential equations, Let T that is equal to capital X, which is a function of a small x only, into capital Y, that will be a function of a small y only, is a solution of equation number 1. Okay. Where here it needs to be emphasized that the x and y are the functions of x and y only respectively. So, differentiating this equation, we will get d by t upon d by x, that should be equal to y d by capital X divided by d by small x, or you can write d by 2t by d by x2, that is equal to y d by 2x by d by x2. Let it be equation number 2, and similarly d by t by d by y, that is equal to x d by y by d by y, this equation number 3. Thus, from equation 1, 2 and 3, thus from equations 1, 2 and 3, we can write y d2x by dx2 plus x d by 2y by d by y2, that is equal to 0. Dividing the whole expression by x y, you can write 1 upon x d2x by dx2, that is equal to minus 1 upon y d by 2y by d by y2. What we can feel by seeing this equation, that initially the temperature by the product of two functions, one is a function of x only, another is a function of y only, but by using the separation of variable techniques, this equation has been represented as in this form, where this is entirely a function of x only and this is entirely a function of y only. That means the variables get separated. That is why this technique is what is called as separation of variable technique. So, let it be question number 4. So, the question number 4, so the equation number 4 it says equation number 4 shows that because x is the function of x only, so day by 2 capital X divided by day by small x2, that will be a function of x only, shows that function f1x that should be equal to y. Mathematically, such type of condition can persist only and only if that both this quantity must be equal to a single quantity, that is a constant quantity. So, this is possible only and this is possible only if constant quantity, a constant quantity. This constant quantity may be positive or negative. This constant quantity may be positive or negative or 0, maybe. Hence, so the equation number 4 can be represented as 1 upon x d2x by dx2, that should be equal to minus 1 upon y d2y by dy2, that should be equal to a constant quantity lambda square plus minus lambda square. Why I am using this plus minus lambda square? Lambda is a real quantity. So, lambda square will always be a positive quantity. Beyond doubt, this lambda square will be a positive quantity. So, in the case if the value is a constant but negative in magnitude, then the minus lambda square should be taken into consideration. If lambda is a positive quantity, then lambda square is a positive quantity. So, under those circumstances, plus lambda square should be taken here in order to solve the partial differential equation, that is a Laplace equation in the 2-dimensional case on the shop floor. So, that is equal to plus minus lambda square. Hence, possible cases of solutions are as follows. Now, the case number 1 is lambda square is greater than 0. Case number 1, lambda square is greater than 0. That is the positive, that is lambda square is equal to positive. So, this equation can be given as d by 2x by d by small x2 minus lambda square x is equal to 0. So, from the course that you have gone through, the differential equation, the x may be given as a small a raised to the power lambda x plus b e lambda x. Type of solution we have gone through in the case of phin also. So, this is cot h lambda x plus sin h lambda x plus b minus lambda x, e cos h lambda x minus sin h lambda x, given as a plus b cos h lambda x plus a minus b sin h lambda x, that is equal to a cos h lambda x plus b sin h lambda x. The second part of the equation, taking the second part of the equation, that is minus 1 by y d2y by dy2, that is equal to lambda square. So, we can write d by 2y by d by small y2 plus lambda square y equal to 0, and in this case the expression which is solution for the y will come as c lambda y thus the solution T that will arrive as a cos h lambda x plus b sin h lambda x into c cos lambda y plus d sin lambda y. Let it be question number 5. First solution, assuming than 0. Now take the case number second, that is lambda square is lesser than 0. So, the case number 2 is lambda square is less than 0. So, the first equation will be d by 2x by d by x2 plus lambda square x equal to 0. So, the x can be written as a cos lambda x plus b sin lambda x. Another is d2y plus dy2 minus lambda square y equal to 0. So, in this case y is given as c cos h lambda y plus d sin h lambda y, and hence t, that is the xx yy, that will be given as a cos lambda x plus b sin lambda x into c cos h lambda y plus d sin h lambda y. The value of those integration constant a, b, c, d, said equations are to be evaluated by the prevailing boundary condition present in a particular problem. Now, we will discuss the third case, lambda square is equal to 0. Now, we will consider the third case, square is equal to 0. So, case 3 is lambda square is equal to 0. So, case 3 is the lambda square is equal to 0, thus d2x by dx2 that is equal to 0. So, the value of x equal to ax plus b. Similarly, taking the second part of the equation number 4, so this equal to 0. So, the value of y will come as cy plus d, and hence the solution, that is xx into yy. So, this t, that is the function of x is a function of x and y is a function of y, that is equal to ax plus b into cy plus d. In this case as well, we have to evaluate the a, b, c and d from the prevailing boundary conditions. Now, the question arises. So, the question arises that how the sign of lambda square is decided. How the sign of lambda square is decided, because this is the first and foremost task, that you should have an idea about the sign of this lambda square, because unless and until you are knowing the exact nature of the value lambda square, you cannot impose a solution for a given case. So, regarding the selection of this sign for the lambda square, there is no clear cut guidelines in any textbooks, but so far as the experience is concerned, so on the basis of experience, some certain guidelines can be sketched. What are those guidelines? So, no clear cut guideline is there, no clear cut guidelines are there. However, one can state that number 1, if the temperature distribution I will solve a problem also in this class. Well, I would like to emphasize that guideline as well. So, the temperature distribution is given along x boundaries, then lambda square should be taken as negative. If the distribution is given along the x boundary, then the value of lambda square should be kept as negative. And on the contrary, if the temperature distribution is given along y boundaries, then the lambda square should be taken as positive. Lambda square should be taken as positive. These are the two guidelines which generally being applicable in most of the cases. So, you can apply at first instance as these guidelines. Temperature distribution along the x boundary, the lambda square should be taken negative, and if it is given on the y boundary, then you should take the lambda square equal to positive. Now, coming to the point that there are so many methods to solve this Laplace equation, the analytical method, the numerical method which is based on the finite difference approximation technique, and the third one is the geometrical method which is based on the concept of the conduction shape factor. So, the question arises, why the different modes of solution, different methods of solution need to be known for an engineer. It means none of the technique is fully proof. There are some limitations of the analytical solution, there are some limitations in the numerical method as well, and there are some limitations in the geometrical methods as well. So, depending upon the situation and circumstances where situation demands the solution of the partial differential equation, Laplace equation, by particular method, an engineer must go for that technique only. And this is the reason that there are so many solution techniques available in any standard textbooks on the partial differential equation. So, let us come to the limitations of analytical solution first. After that, we will discuss the problem today at the last. So, come to the limitations of analytical solutions. Limitations of analytical solution. Number 1, even the method provides almost exact result so far as temperature distribution is concerned. Temperature distribution is concerned, but the solution becomes exceedingly difficult, but the method becomes enormously difficult in the case of irregular geometries, in the cases of irregular geometries, and hence the complicated boundary conditions from there, complicated boundary conditions arisen from there. So, under these circumstances, when an irregular geometry is there, so it is very difficult to conduct the analytical solution in that case, because the nature of the boundary condition is so much confusing as well as complex in nature that you can never arrive at exact solution of the of the Laplace equation in those circumstances. So, in the case of irregular geometry, basically this method fails. Number 2, sometimes series solution is obtained for which it is very difficult to evaluate numerically. So, these are the limitations of the analytical solution. So, now let us consider the case of a semi infinite plate and let us see that how the temperature distribution that particular case can be determined by using this analytical technique. So, the illustration of this analytical technique, this is the last thing which is to be covered in the present class. So, illustration of analytical solution. Illustration of analytical solution. A semi-infinite plate of width L length is tending towards infinity, is tending towards infinity, that is the meaning of semi infinite system. A semi infinite plate of width L and the length is tending towards infinity. In which one side is subjected to a temperature T, that is a function of x, that is the temperature distribution will be given along the x direction, and the other sides wall temperature is maintained at T is equal to 0, is maintained at T is equal to 0. We have to obtain an equation for temperature distribution, for the present case. This is the problem, a simple illustrative problem that you have. Here, in order to solve such type of problems, so let us try to visualize this problem as this is the x axis, this is the y axis, and this is the semi infinite plate, this is tending towards infinity. This temperature around the x boundary that will be given T is equal to Fx, and other side of the wall is maintained at the temperature T is equal to T naught. So, this is the case, and in this circumstance you have to obtain a temperature distribution equation. So, first the boundary conditions are number A, x is equal to 0, t is equal to 0. Number B, x is equal to L, t is equal to 0. Number C, y is equal to 0, temperature is a function of x. And number D, y is equal to infinity, t is equal to 0. This is the boundary condition as the present problem. Since the temperature has been given on the x boundary, so lambda square value should be taken negative. Lambda square may be taken as negative, hence solution of t is equal to a sin lambda x plus b cos lambda x into c to the power lambda y, or put here minus c to the power minus lambda y plus d e raised to the power plus lambda y. Let it be question number 1. Now, put in the boundary condition number A. X is equal to 0, t is equal to 0. That means this is equal to 0, that is A, this is 0 plus B cos lambda x is equal to 1, c e raised to the power minus lambda y plus d e raised to the power lambda y implies that the value of the integration constant b is equal to 0. Okay. Now, put in the boundary condition number D, that y equal to infinity and t is equal to 0. So, imply that, so here you can write the value of t, that is the a t is equal to a sin lambda x into c e raised to the power minus lambda y plus d e raised to the power lambda y. So, t is equal to 0, it means a sin lambda x, so this is equal to 0, d e raised to the power lambda infinity, that should be equal to 0. It means the value of the integration constant d, that needs to be equal to 0. So, b and d has been evaluated. Now, taking the third boundary condition, that is the, now so taking the second boundary condition b, that is at x equal to L, t is equal to 0, it means a sin lambda L into c e raised to the power minus lambda y equal to 0. So, you cannot evaluate c equal to 0, rather you should evaluate sin lambda L is equal to 0. So, the value of lambda L is equal to n pi. So, the value of lambda is equal to n pi by L, that is lambda is equal to n pi by L, where this n is equal to 1, 2, 3, etc. So, only the boundary condition number 3 is left, otherwise all things have been utilized. So, coming to the boundary condition number C, that at y equal to 0, t is equal to f x. So, put here f x is equal to a sin lambda equal to n pi x by L into CE raised to the power minus lambda y, that is minus n pi y by L. Okay, that can be written as A into C into e to the power minus n pi y by L sin n pi x by L Now, y is equal to 0. So, this quantity can be given as A into C, this one to 1 into sin n pi x upon L. So, putting y equal to 0 here. So, the temperature distribution can be given in the present case as, so temperature distribution for the present case may be given as Fx is equal to C dash sin n pi x by L, where C dash is equal to A into C. Because of the fact that this is a harmonic solution, so for each and every value of n there will be value of AC. So, in that case there will be so many values of C dash. So, in a summation we can write here summation Cn dash sin n pi x by L, okay, where this Cn dash, where this Cn dash can be given as 2 divided by L integration from 0 to L from the Fourier series Fx sin n pi x by L into dx. So, the complete solution is Fx is equal to T is equal to Fx, that should be equal to 2 by L summation n pi x by L exponential minus n pi y by L, this quantity, into integration from 0 to L Fx sin n pi x by L dx. So, this is the solution of the temperature distribution for the present case. So, we have discussed today the analytical solution of this differential equation, that is partial differential equation, that is the Laplace equation. In the next class, we will try to discuss the numerical method or the finite difference approximation technique for the solution of this partial differential equation, as well as we will go through the geometrical method as well. So, in the next two classes or in the next class itself, I will discuss both the technique in one class, and once this Laplace equation will get over, then we will switch on our study towards the unsteady state heat transfer. Thank you.